Hi, this video is about completeness axiom. And after my dead body, are you going to think that completeness axiom is trivial or obvious or that it doesn't have a lot of drama around it? This whole video will be dedicated to building up drama around completeness axiom, which is well deserved, in my opinion. So, and also this idea, obviously I got from the textbooks that some of them do build up the drama around it, and I do like it. Okay, so let's get started with the simplest definition of the completeness axiom and then improve upon that. It says, the real number line has no gaps. But you've been operating under this assumption that real number line has no gaps your whole life. So it might seem a little bit trivial, but it's not. So when you will learn about completeness axiom in your books or in your lecture, sadly, another thing still to show very quickly after the definition is mentioned, and that is the supremum or the least upper bound or the greatest lower bound. And they're interesting, but they're just technical definitions, and we're not going to spend any time on that because we're going to talk about a deeper idea, and that is completeness axiom. A real number line has no gaps. Some of the best mathematicians of 19th century spent the entire 19th century to build up, construct a real number line from the rationals, starting from 1800s by Cauchy, and successfully ended. The idea was already there in 1872, thereabout, by Cantor and Dedekind. And the modern definition, the one that you find in our textbooks, and the name completeness axiom was written down by Hilbert in 1900. But also humanity took that long to have completeness axiom, which is something that you can't do without. In some of the most classic proofs in analysis, the completeness axiom is integral part of that. You can't move on in those proofs without it. So it was critical to have that. And why do I say 2,500 years? Because the square root of 2 is irrational, which is always part of the chapter of completeness axiom, was proven by the ancients, the Pythagoreans, in 5th century BC. So the proof was almost identical to the modern proof that we see. So they knew that was irrational, but the completeness axiom did not come until much later. So what do we mean by there are no gaps on a real number line? And what are the gaps? And on what number line are there those gaps? The rest of the video will be about that. Let me show you the real number line first. Here is the real number line. That square root of 2 as well as all the other rational numbers are comfortably there. There is that solid filled dot there, square root of 2. And here is the rational number line. This has Q there. Notice that it's no longer R. And it is missing every irrational number. This whole video, I just picked one irrational number, but the arguments would be identical about every other irrational number. What do I mean when I say it's not there on a rational number line? This is exactly what I mean, and you need to follow this mental exercise here. It might seem weird because the arguments will be about chasing or approaching a value on the number line and it not being there or it being there. And this might seem peculiar to you, but it is deliberate because this sort of arguments are coming up in this course soon, so it's good to get used to it. Okay, so imagine I give you a project to build a structure made out of Lego blocks. So this is easy. That has a length of square root of 2, and I will measure it with other 2 line segments I will make a triangle, and it has to be square root of 2. So I give you the building blocks, because that's the whole caveat. And the building blocks I give you, the Lego blocks I give you, their length is rational. The dimensions are rational. So you get to building and you take the first block that has a height of 1, and take a second block that has a height of 0.4, a third that has a height of 0.01, and so on. And you get 4 decimal places, and you say, well, I have many times done with less decimal places in my life, substituting a rational number with a rational number with much less decimal places, so this should be fine. And for algebraic calculations, that's fine. But for analysis, rational numbers are categorically different than irrational numbers. So anyway, you get the 4 decimal places and you say, this should be good enough. And you come back to me and I look at this and I tell you, well, you can't reasonably argue that number 1.4142 is the same thing as number 1.41421. These are 2 different things. And you say that's a little petty, but I guess that's fair. And then you go back and you improve on your project and you come back with 50 decimal places. And I'm able to come up with 51st decimal place and tell you these 2 numbers are not the same. And I'll be right. because the game I gave you was impossible. It was rigged because you cannot construct irrational length using finite sum of rational numbers, meaning that square root of 2 is unattainable on a rational number line. You can zoom in on that interval, that neighborhood from 1.4 to 1.5. You can zoom in on it. You can approach square root of 2 really well, annoyingly well, like 50 decimal places or even more, but not exactly grasp it or have it, which is the number line that definitely has it. And that's the real number line that closes those gaps, that those gaps are patched up, and square root of 2 is certainly there on a real number line. So this picture right here shows you exactly what the completeness axiom is, but in a picture definition, right? So you can take a picture of it, and this is good for a definition. The only problem with this picture, and I definitely want you to not confuse this, is that from this illustration, you might think that there are so many rational numbers. There's a whole line of rationals, and then there are few irrational numbers that are sprinkled over it. And that's not the case. The opposite is true. There are more irrationals, so cardinality of irrationals is greater than cardinality of rationals. They're both infinite, but irrationals are uncountably infinite and rationals are countably infinite, okay? But they're equally dense. On any interval between any two reals, there is a rational number, and between any two reals, there is a rational number. And you will prove each one, both cases, quite soon after this chapter. So the density of them on any interval is the same, but not cardinality. So this picture is deceptive in that exact way, but successful and effective in showing you what completeness axiom is. Okay, so we have a complete number line. Who didn't have a complete number line? Everybody before completeness axiom. Okay, so when the Pythagoreans proved that square root of 2 was irrational, and as I said in the beginning of the video, in a very similar fashion that we see it today, they had to think about what was square root of 2. Is it a number or what is it? Because they came about it from geometry, which is like, this is real, right? There are two line segments and the hypotenuse is square root of 2. Okay, it's undeniably there from geometry. They proved it was irrational, so they did know that. But for them, numbers were rational, period. They didn't compromise on that. They didn't expand definition of numbers. They said numbers are rational, period. So then they were forced to accept that number was a weaker notion. And by that, I mean it was a smaller set than length. So length included things like numbers and then some. So numbers were a proper subset to length. And today, the modern project was to pair up every length on a number line, every line segment on a number line to a number, and vice versa. Every number to a point on a number line. And that type of a handshake has been accomplished. We certainly have that. And the reason why you need to have that, and this is a type of a qualitative argument about the nature of a real number line. Big girl definition of the completeness axiom says that any non-empty set of reals, if it has a upper bound, if it's bounded above, then it has the least upper bound. And the least upper bound, what you need to know now, is that it is the smallest of all upper bounds. And it's smallest, meaning it is one unique value. It's an actual one specific number, different for different intervals, and it will be different for different sets, but it is one concrete number. So you're basically saying that some arbitrary interval that is just not empty and is bounded above has and possesses this specific number. And you could never say that type of a statement if you were making that argument about such a number line that possessed a lot of gaps, okay? You can only say that sort of an argument as a responsible person if you were talking about a number line that has no gaps. Because what if, God forbid, that least upper bound falls on, in our case, on square root of 2? You saw that rational number line missed that. You could approach it very well, but it wasn't exactly there. So this sort of an argument cannot be made about rational number line. And the completeness axiom, the formal definition of it, hinges on the nature of the real number line is such that it has no gaps. So this gives you all the assurance you need to make this sort of a claim about an arbitrary interval that you don't know where it's at. And you will be using this exact statement many times in your proofs. And certainly some of the very fundamental theorems have this axiom as a undeniably inevitable part of them. You can't do without those proofs without this axiom, okay? So it's pretty important. I hope that you enjoyed this video, and I see you in the next video. Bye!